Professor Muhammad Sharaf with you. Our lecture today is about a flat plate solar collector for water heating system. First of all, we have to go to your destination folder from here. Okay, don't open your model from desktop. You have to go to your destination folder by assigning your drive folder, your working folder, and so on. Okay, you have to double clicking. Okay, this is our main model. It's simple. It's about it is not only a flat plate solar collector, because we already demonstrated this that before. Our subject today is about solar flat plate collector system heat for water heating. Our system consists of we have flat plate solar collector with a thermosiphon concept. We attached a small tank for each unit, and we have here recirculating pump. Because this is ethylene glycol in this cycle, and we're going to transfer our thermal power via heat exchanger intermediate unit. And this is our water tanks, water storage tank with normal recirculating pump. Pumps should be powered by photovoltaic system. Okay, you can remove this or you can add it, it's up to you. So we have here, this is inlet cooling water to the system, and this is desired output heating water to the building, to the user, to the thermal application, whatever. Okay, and we have here, this is our intermediate heat exchanger between ethylene glycol and water side. Okay, going from here, please check for model browser, check all of this. Okay, what we have here for plate solar collector, let's go and assign some inputs. What is our main operating hours? Okay, what is normal or average solar radiation, watt per meter square? What is your average wind speed? Let it be. Okay, ambient temperature, your ambient temperature. I will stick myself at 25. Okay, this is for operating conditions. For design, what is your thermal load? Thermal load means your storage tank. Suppose I'm going to use normally it's around for each unit it's around 75 liter or up to 150 liters. Okay, as a storage tank size. So suppose I'm going for 150 liter. Okay, for ethylene glycol, what is your ethylene glycol percentages or volume? Because it's some kind of a fluid mixture. Suppose I'm going for 30% of ethylene glycol. Okay, okay. For some specifications, what is your design specifications? What is your flat plate glass cover? Glass covers, number of glass covers. Okay, one glass cover, two glass covers. Okay, let it be one as usual. Tilt angle, I think 45, 30, it's around something like this. It depends on your design. Glass cover emittance, okay. Plate emittance, plate inside. Okay, aluminum, it's aluminum or copper or whatever. We can assign some losses. I will keep these things. Bottom losses, tube spacing. Okay, as you can see here, this is the tubes attached to the plate. How many tubes per each module? How many? So I mean, you can assign how many tubes by assigning the spacing between each tube. So suppose it's 10 centimeters. Okay, a tube diameter in centimeters. Okay, a plate thickness in millimeter. Okay, plate material thermal conductivity, suppose it's copper or aluminum, you can assign this one. Okay, so our model is ready for this. For heat exchanger, so we need because this is a design model, so we have pumping system efficiency, because there is a pump inside here or attached to the tank for recirculation with a flap collector. So pumping efficiency around 85, effectiveness it's around 85 or 80. Okay, suppose it's 80%. Ethylene glycol percentage volume, I will keep it at 60%. What is the diameter of your heat exchanger? You can optimize this depending on your loads. Okay, let's hit apply. Okay, for hot water storage, suppose I have to deliver within 24 hours. Okay, ambient temperature is the same, wind speed is the same. Okay, and okay, inlet storage temperature, inlet stream of the water goes to the storage. So I have to assign this, Control M, and going here, we can reform this from here. Inlet water storage to storage temperature. Okay, this is we are talking about this stream. Suppose it's around 15 degrees Celsius. Okay, 15. Okay, suppose it's in winter or something like this. Outlet storage temperature, your desires. I have to reform this too. I have to reform. Let's going here and going to outlet water. Okay, water. Okay, comes from heat. I'm sorry. Okay, let it be as it was. Be as it was. Okay. Okay, I'm talking about this. This is outlet coming from the heat exchanger. So we have inlet here assigned, and this is top temperature. Let's go for here. Suppose it's around 65 degrees Celsius. Okay, and okay, inlet storage comes from I'm sorry. Yes, this is 65. Okay, comes from the heat exchanger, and this is our desired, supposed to be lower than this one. Okay, I have to configure this, going here. Okay, this is outlet storage. Yes, this is outlet water storage temperature to the user. Yes, this is our desired temperature. Okay, we have here this is our desired temperature or design temperature. Suppose we need storage tank medium at 55. Okay, and inlet storage comes from the heat exchanger. It's around, it should be greater than this, therefore it's around 65, something like this. Due to thermal losses, you can optimize this, sure. Storage tank volume, suppose I need 300 kilograms or 200 kilograms. Let's go for 200 kilograms. Okay, and your tank diameter, we will see the effect of tank diameter. Okay, insulation thickness, this is insulation thickness of the tank. Thermal conductivity of the insulation. Storage tank, there is a pump attached to the tank. Okay, so this is the efficiency of the pump. Okay, for photovoltaic system, you can choose between watt per meter square or kilowatt hour. Let's go for per meter square. So I have to assign some inputs. Operating hour, suppose it's 8 hours for circulation, and solar flux it's around 500. Design, suppose it's 280 watt module. Okay, performance of the battery, cost of the battery. Okay, we will leave these things. Okay, now we prepared our model, and now it's ready for running. Okay, let's hit run and see our results. We can run this dynamically or single point iteration. Okay, let's see and discover some outputs. Okay, let's run, finish. Okay, let's go inside here and see our results. Okay, for flat plate solar collector, this is the plate temperature. It's around 95. Mean plate temperature, it's around 59. This is your module area of solar collector. Okay, it's around 1 point. Okay, let's go here. Okay, I'm sorry, I have to go here, and I think yes, I have to assign this one. Tank volume, it's around, yes, let it be here in order to adjust the mass flow rate of the cycle. Okay, let's go here. Because it's 24, we need this for 8 hours. Okay, okay. For this is our this is collector area. It's around 2.5 square meter. Okay, and total solar feed area it's around 7.5 square meters. Okay, this is thermal load on the flat plate collector, heat removal factor, efficiency factor, fan efficiency, flow factor. Number of flat plate collectors should be used. It's around three units. You have to use 3 units of this one, 3 units. Okay, attached to the system. Okay, let's go for heat exchanger. Okay, this is outlet temperature from the flat plate collector should be, it will be calculated at or stated at 75 degrees Celsius. Inlet temperature to the flat plate collector is around 35. I'm talking about this. This is inlet to the flat plate collector, and this is outlet from the FBC. So it's around inlet at 35 and outlet at 75, quite normal. And we have, this is total mass flow rate to the cycle. This is your total mass flow rate, heat exchanger area, and this is your pumping power. Okay, let's go for hot water storage tank. Okay, for hot water storage tank, outlet temperature to the heat exchanger is around 25. We are talking about this one here. Yes, this temperature it's around 25, and this is 15 degrees Celsius. This 15, so the input here is 25, and the output here, we assigned this before. Okay, let's go here again. It's around 25. This is storage circulating mass flow rate. Okay, and this is thermal storage in kilowatt power. Thermal losses to the ambient. Okay, and pumping power, and this is the tank height. Okay, it depends on your diameter of the tank or something like this. Okay, let's go for some dynamic modeling. Okay, I will assign this infinity, okay, and let's say changing some parameters. Double clicking here first, I'm sorry, and going inside, and I'm sorry, I have to do it again. I have to do this again. Okay, going inside here and hit apply. Let's hit run and see the effect of our result. If we intended to increase the storage volume, okay, let's see our effect. Let's hit run. Okay, I'm trying to increase the outlet water temperature to the user up to, okay, increasing the temperature, and storage heat exchanger temperature, I will increase it up to 70 degrees Celsius, so the user gain should be around 60. It's let's increase the tank volume, okay, 20 meter cube. Let's increasing up to 50 meter cube, okay, as a volume. 80 tons, 90, 100 tons, okay, let's stop here and see our results. As you can see here, because we changed our temperature, therefore there is a slightly change in mean billet temperature, okay, and this is I have to remove this one, okay. There is some kind of changing in collector area, as you can see, increasing the collector area, okay, and increasing, this is total solar field area, okay, massively increased because we increased the total mass flow rate, so the cycle, thermal power, fan efficiency, overall heat losses, and so on. You can also discover your results from here. Let's go here and discover some results from data inspector, as you can see here. Okay, this is your plate temperature, mean plate temperature. This is your flow factor. Okay, it's between 0.6. okay, this is your flow factor. This is solar field area, so module area. This is your module area. It's around 3 meters per module. This is your total solar field area, and this is your thermal load and total mass flow rate. This through the solar field, through the module, and this is overall heat loss. It's between and 6.4 is your thermal losses, and we can add more results if we would like. Okay, let's go for heat removal factor. It's between 0.6 and 6. Okay, you can optimize your design in order to get because if this one reached to 1, so that means that your system is running smoothly and very nice, most efficient. This is efficiency factor, and this is your fin efficiency. Okay, number of solar collectors. Okay, and we have here, this is your module area, total system area. This is your total system area for photovoltaic, because this is for photovoltaic. Okay, and photovoltaic area. Okay, I forget to go inside photovoltaic and see our results. So For pumping power, we need around total module area is around 3 meters, and the total system area is around 70 square meters. Okay, for this power, it's around 5 kilowatts. 5 kilowatts for this input for 100 meter cube, as you can see here, 100 meter cube, as a huge 100 tons of for hot water you're gonna use by this system. So you have to design your system based on your what is my ideas, what is my recommendations, how can I optimize my system. So you can easily by selecting your best operating conditions, so you can get your results, optimized results according to your area, and this is your photovoltaic cost. You have to pay for photovoltaics around 8,400, okay, or 500, okay, and this is for black yes, it's around 59. Mean plate temperature, okay, heat exchanger, okay. So the outlet temperature, outlet flat collector temperature is around 81, because we increased the system design temperature to the user. Okay, so if you increase the desired operating conditions, so the design operating condition will also change. And this is your outlet, it's around 36. This is again from your flat collector. It's from, again, it's from 36 up to 81 degrees Celsius. Hopefully, I would like to thank you that you enjoyed my videos, and I would like to thank you for your interest in our REST library models. Don't forget to like, share, and subscribe. Thank you very much.